Good morning, all my dear students. Now, in this session, I would like to give a big canvas on which the graph traversal methods make a sense, and thus we find an inspiration to learn these methods. So, the plan for the session is firstly we'll have a quick recap of the graphs terminologies, and then we will understand the traversal methods, depth first search, breadth first search, and very importantly, their applications. Now, the first and foremost is, why should somebody study a graph algorithms? Why is that graph is so much importance for a computer science students? The first reason is, there are thousands of applications in the real life which can be better represented using a graph. And computer guys are not the first persons to work on graph. So the mathematicians have worked pretty lot in this graph and have developed several methods to solve commonly encountered problems in graph theory. And the graph provides a very interesting abstraction to the system that we are trying to represent. And all the more, a challenging task is this. Anything challenge would certainly excite we guys to come out with a better solution for the problem. Graph, the simplest way to define a graph is G is equal to V comma E, where V is a set of vertices and E is a set of edges. The edges connect the vertices. Now we will understand the few applications, real life applications where graph is used. The first one is protein-protein interaction network. This is used by genetic study, wherein every vertex represents a protein, the edge represents the interaction. So to come out with to understand the physiology and hence to come out with a medicine or to study the mutation, one would really need this protein-protein interaction. And we know this is certainly a very, very large number of proteins present and a lot of interactions happening between these proteins, and thus this is a huge network there here for which this can be better represented using a graph, and we must really have good methods to work on this huge network or huge graph. And now of recent COVID-19 they here, and they say that it has already gone mutated, and genomics and this kind of study is now being carried out by the scientists to find out a medicine, a vaccine for the COVID-19. The second application is the internet as mapped by the Opte Project. Herein, the internet is a network of computers or any computing devices, because now the device is not just a computer, it can be a mobile, it could be a sensor, it could be an iPad, anything which has and it could even be the fridge or the oven if it is connected through a sensor to the cloud here. Now, we would want to find out all these devices and their interconnection, and each device will have an IP address, so that the IP address is also shown there here. So we see how huge the network is. So is the next one, map of science clickstream. Clickstream is a new word that you are getting for the first time. Clickstream is nothing but every time that I click on the mouse or I press on the pad there here while I'm traversing through the internet there here. Say you're doing a shopping, the first thing is you would want to choose the category of some kind of books that you would want to purchase. Is it a literature? Is it a technology? So you would make a click. So that will be recorded. And when you go to technology, is at which domain it is and so forth. So that every next step will be through a click. So all such clicks by every user of the internet will be recorded. So this will be used to determine or to find out what is the psychology or what kind of the commodities are the users buying there here, what is his behavior and so forth. And herein it is the science clickstream. That means that so the clickstreams are to the web portals wherein all the information about science experiments, it could be the data, it could be the results, it could be some papers, all such are stored here. So from here, if you want to learn something about a COVID-19 research that has been done there here, every click of mine will be recorded, and this figure shows the each web portal that has scientific data, and then the edges is every click stream that the user is clicking on. So even this is a huge network or huge network of those clicks. And this is what everyone would love to. So this is the Facebook friends, and the Facebook friends, what we see is that a network, every user, every person is a vertex, and then two persons, a friend of each. If they are directly friendly here, I will have an edge from the person A to person B, indicating that the edge represents the friendship. And then you see that you have all those rays coming in, which are nothing but the edges they here. So person from US, and is also a friend of a person in India they here, more specifically Karnataka, and more could be in Hassan they here, right? So all such are represented, and you see a huge collection of the edges they here, and here the vertices are so dense, that means that we don't see a dot, rather we see it as a complete painted like a white they here. And we also see is that this friendship is much more in USA, and here also in India they here, very less in Africa, and much better in the South America and so forth. So such is a huge network, and you can think of processing, doing some work on the social network. Now we could really understand or appreciate the use of graph in real life, the problems they here. Now how will I represent these applications in the form of a graph? So for a communication network they here, my telephone, a computer, or every computing device will be represented as a vertex, and the cable laid out between these two will be represented as an edge. And if I'm trying to model a circuit there here, every gate, register, transistor, processor will be represented as a vertex, and the connection, the wiring between them will be represented as an edge. And similarly, so they here we have for several other cases. Now, the next thing is, before we really delve into the graph traversal methods, we need to get familiarized with the terminologies of the terms, because that makes very easy for us to converse, to communicate our ideas. So this is a graph, and you see that this is an edge, this is a vertex we already know about, and then we are getting these to the terms path and a cycle. Path is nothing but a sequence of vertices. So I can have a path there here, so from here I can have this path coming over to here and there here. So from here to here, this is of edge 1, second edge, third edge, fourth edge. Can I say that this is a path of the length 4? And now here and say I see it's also a path, but then we get back to the vertex from wherever we started. So such closed path, we call it to be a cycle. And this is one, the whole thing is a graph there here, but you see that this part, any of these vertices are not connected to any vertices here, and also similarly the vertices here are not connected to this. That means that this is one component, this is another component, this is the third component. The whole graph has got 3 connected components. When I say a connected component, connected, it means that any vertex, it's possible for me to connect to or go to any other vertices. If so, I call that to be a connected component. So these are the few terms they here, the degrees and so forth, you are comfortable. So the terminologies are edge, a vertex, a path, a cycle, and then the components. Now, what kind of a problem are very frequently encountered? So the frequently encountered problem is there a path between S and a T, that is two vertices? Say for example, say in Hassan they here, so we have several number of cities, villages they here. These are connected by roads. Now let's say that the DC wants all the state highways in the district of Hassan they here, and which cities or which villages are connected by through this state highways. So then, so the DC would want to find out, is there a state highway between say some Shantigrama to another place, Tamblapura. So you would want to find out, is there a state highway between these two? That is there a path, is there a road wherein I can traverse from Shantigrama to Tamblapura, going through only through the state highways, right? There's a path. And the next one is, certainly there could be several paths taking me from Shantigrama to Tamblapur Desho. Probably I am a smart guy, I would want the shortest path. Is there a way that I want to find out the shortest path between any two vertices in the graph? And the next thing would be of interest is cycle. Does this graph has a cycle there? So now what happens is that, so the DC would want to have a tour of different places they here. So you would want to cover few places in a day they here. So we'll start from Hassan they here, visit few the cities or the villages and comes back. So does there exist a path or a road wherein we can start from Hassan, visit few and get back to Hassan? That's a cycle, right? And then the cycles, we have this Euler tool and the Hamiltonian tool. Euler's tool is that every cycle wherein each edge is visited exactly once. Hamiltonian tool where each vertex is visited exactly once. And then we would want to check connectivity. So now probably some want to see that DC would want to say that all the villages, Gram Panchayats of Chandrapatna district, Chandrapatna Taluk, they here. Now is there a way that they are connected only through the state highways? So now we can check that are those vertices are connected. Now the next thing is he really would want to connect those Gram Panchayats they here, but then with using minimum total distance. So then we would want to find out minimum spanning tree. This is a very important one which we would be studying in the future chapters. And the biconnectivity, planarity, graph isomorphism, several more things we will not worry at this point of time. Now as the next, we could list several number of problems. Now the question is, which of these problems are easy? Is it difficult? Is it impossible? Is it intractable? And so forth, right? So the challenge is that am I able to see it with my eyes? But then if I want to work on this, I'll have to store this graph in the computer. The computer, where do we store it? It's in the memory. How do I store it? What data structure do I use? Being in the case of this matrix they here, I should have read through the complete row and find out which of them there is an edge between. Certainly this is only a 12 cross 13 cross 13. Had it been 100, then I'll have to go with the row with complete 100 entries, or if it were to be 1000 or a 10,000, certainly it takes much more. So what would be decided? So we had all initial setup there here. We did understand the why what is the importance of graph there here. The second thing is the terminology is being used. The next one is how the graph is stored in the memory, and what kind of problems are generally addressed in a graph there. Now, when I have a graph, very often the first thing that I would want to do is traverse through the complete graph. What do you mean by a traversal? Say I go to a new place and I would want to travel. That is, I would want to visit every important place in that particular, every important landmark, every important sightseeing place in that particular city. So I would want to visit all the vertices of a graph. So that is what is said to be a traversal. Indicates that you would want to visit all the vertices of the graph there here. So there are two ways in which I can do it, either using a breadth first search or using the depth first search. Here comes a puzzle, right? I'm sure that all of you would agree that each one of us have solved this puzzle while we were kids, and nobody needs an explanation of this puzzle. Certainly, we have a monkey, and monkey, what it needs is a banana. Now it has got to go through this maze in order to get this banana. So it can only go through. Now if we take this path here, now I got really stuck. I cannot go further. So I'll have to look for other ways in which I can go, and then so forth here. So that we used to try on this. We used to solve it on a sheet of paper with a pencil here. We used to try all several ways here, and by fluke we would get the answers in a first or second trial, or we'll have to do it several number of times. But then can I do it in a more systematic manner so that I can get the solution every time? So this is one possible solution that is being shown. A path from here, from the monkey, the entry to this particular exit gate wherein the monkey would be getting this. Now this kind of a problem I'll be able to solve if the size is small, and then if a man has to solve it. But now what I want is, I want a program, I want a computer to solve it for me, and moreover, if this is to be a huge one, I will certainly get lost, right? So I want some systematic method of trying all possible ways in order to reach out the treasure or to exit out of this maze. Now the next is, if I have to develop a solution to do this, now how will I represent my maze as a graph, right? That's the first thing that I need to answer. Well, this can be represented by means of a graph. What I then do is, so this is the junction point, intersection point. Such intersection point, because from here I can go left or I can go to the right and so forth. Here also I can go like this or I can go like this, right? Each such intersection point are represented by vertex, and this is my path that I can take, right? This is one path, this is another small path. All such passages that we see here are represented by edge. So it's so easy, so interesting to see the maze problem being transformed into a graph. Now all I now need to do is, how do I traverse this graph so that I can go from the start vertex to the exit vertex? So one way that I can really devise a method to do this is, so I would want to try all possible ways. To do that, I can just roll out a ball, so that the ball will really start rolling as long as there's a passage. So from here it gets rolled here. Now I also would want to see the path that it traces. So that to do that, what I can do is, to this bar I can tie a string, so that as it rolls it leaves the string behind it. So then it goes, yes, this is the path traced by this is the string that we see with the ball here. From here it can either go this way or this way. Say I take this road randomly, I go over here, right? I come over here. As the next is, from here there's only one option here. So then it really goes there, right? And then certainly it is gone, it is a loop here, and there's no way that it's come out. So then it says that it's not the answer, so that you come back, right? From here, are there any other paths to be checked? No. Then you go back, right? And here you see that this path was not checked. So now let me take this path. From here you go there here, and from here you're again struck, right? So you go there and again you backtrack, come back and see from here, is there an untried path? Yes. So take this path and you'll be out of this. So there's a simple way to understand, one very good way to traverse through this in order to exit out. On similar lines is this traversal depth first search is proposed, right? So I start from a vertex, I go to its neighbor. As soon as I find a new neighbor, I start exploring that vertex and I keep doing it, right? So I will not get into the algorithm because you already feel of it. Now I'll just quickly take you through that. So this is the source vertex and find L. So I'll start from S there here. So from here S I can go to A, B, C, but I shall randomly choose A, and as soon as I visit A, now what I do is I start exploring A, right? And then I come to D. Now as soon as I come to D, I start exploring this, and now from D where I can go, now I can go to B, yes, because it's yet been unexplored. From B, yes, no, it's already been visited, I come back. From here where where can I go? I can go to C. Yes, that was not visited. So I do this. So this DFS that you're going depth-wise there here, and this is for the people who are brave, who can really take risk. So that's the general idea of DFS. Now the breadth they here, so it is this is for very cautious people. So I start from this, I visit all its neighbors, I visit A, then visit B, then visit C, and there are no more adjacent. I stop over here. Now I start exploring each one of these. I explore A, from A I go to D, and there are no more. I go back, start exploring B, D is already visited, done. I go to C, right? This is BFS. I am really not getting in the details because you were already given the videos using which you will be able to. Yes. Now, the very important thing is the applications of DFS and the BFS. How do I use this to solve the real life problems, different applications? Because we are worried more on the application aspect rather than memorizing the algorithm. So now I shall take you through this connected on the applications. The first thing is, so when I say this application, this can be done either by the DFS or by the BFS. The first thing we will now see is I can use this BFS or this to check whether the graph is connected or not. So that means that now for the DC has got few gram panchayats. Now he would now want to find out, and he has got the graph which represents the state highways connecting thus. So that he has got say 10 villages there here. Now he has got a graph, the graph of the state highway connecting this, right? Now what I now do is I apply DFS. When I apply DFS, I will know how many vertices are in a way, how many gram panchayats are visited. So and I shall say that as in this, I shall report to the DC that 6 gram panchayats are visited. So he knows that he had 10 gram panchayats and now only 6. That means that all those gram panchayats are not connected, right? So this is how I can check the graph is connected or not. What I'm going to do is, given the graph there here, apply DFS, count how many number of vertices you visited, and then you also note the total number of vertices the graph has. If both of these are equal, then the graph is connected. Now if this were to be the given graph and I apply the graph, the DFS or the BFSL from this, now I visit 2, I visit 3, I'm done, and I report that have I visited 3 vertices, but then I know that my complete graph has got 6 vertices and he was able to visit only 3 vertices. That means that the graph is not connected. That means that DFS or BFS can be used to check whether the graph is connected. Now, if it is not connected there here, now I also would want to find out how many connected component does the graph has. Now I'll have to find the connected components that the graph has. Now to do this, again I can use this DFS or the BFS. So what do I now do? So this is my whole graph with 13 number of vertices. I apply DFS or a BFS from the vertex 0. And this is my traversal. I'm done with that. Now, and I say that I report back after completing my DFS, I say that have I visited 7 vertices. But then I know that there are 13 vertices. So then the boss tells me, DC, apply again the DFS from one of the unvisited vertex. So then I should choose the vertex A, 7, which is not visited. I apply DFS from here and I go to 8 and then it's done. And I again report back to DC that, sir, 2 vertices or 2 gram panchayats are visited. And then he's still not satisfied. He says that, yes, there are few more gram panchayats. Apply DFS again. So I'll choose this 9 and again apply, call DFS to the BFS, and then I should say that there are 4 vertices visited using a BFS. Now I say report back to the DC. So DC knows that I applied DFS once here, second time here, the third time here. Did I call DFS 3 times? It indicates that the complete graph has got 3 components, right? So I can find out they connected the number of components and the components themselves by using DFS or the BFS. How do we do that? You apply DFS or a BFS and you just pick a vertex and start doing a research from that vertex traversal. And any vertex is unvisited, apply DFS again from that particular vertex. Repeat this process until all the vertices are visited. The number of times you apply DFS or a BFS will give you the number of connected components that the graph has. Now this is another example, the same thing being shown here. So this is representing a network, the dots representing vertices, these lines representing edges. Now my application of this the DFS or a BFS will tell me that this is one component, this another component, this component, and so forth. I'm sure that we all of us would agree that we would not have been able to do this manually with so much precision. So the algorithm does it for us. Any small component can also be determined with the least amount of time. Now the next one is the other application is now the DFS. The DC would want to find out that is there a state highway from, say it is from Chandrapatna to say Chandrapatna to, where should we go there here? It is Chandrapatna to, not getting a place there, say Balapete. Is there a straight highway connecting that? Yes, and probably this is the graph which representing the state highways of the entire Hassan district, and I'm sure that Balapete is on the road from Hassan to Sakleshpura there here, right? You also know the Chandrapatna. So now he has given us problem. What I now do is I apply, this is my source, I should say this is Chandrapatna. I apply the DFS from here, and this is what it goes. And then probably what I'm looking for is Balapete. So B standing for a Balapete. So I came over here. Now I can stop it and say to the report to the DC that yes, there is a path from the Chandrapatna to Balapete. Right, so that the DFS can be used to find out the presence of a path. That is what I have to do is, given a source vertex, I'll apply the DFS, keep visiting the vertices until I find that particular, until I visit that destination. Right, if so, and after the completion of a DFS, if you still haven't visited the destination, you say that yes, there is no path between the source and the destination. And the next one is you want to check whether the graph has a cycle or not. That is, we said that our DC would want to go on a touring day here, visit few cities day here, and then here all along the state highway, and then he will start his tour from Hassan, visit few cities, and then come back. So now, and then he doesn't want to take the same route the second time day here. So then is there a cycle day here? Yes, you already know that the DFS or a BFS traversal will indicate the presence of a cycle if there is a back edge for a DFS, the cross edge in the case of a BFS, right? So herein this is the cross edge telling us that yes, there is a cycle, and here this is giving us a back edge. Even this indicates that the graph has a cycle. So very easy to detect whether the graph has a cycle or not using DFS or BFS. Now, we will now clearly list down all the applications of DFS, because whatever we studied, we said so far, are applicable for both DFS and the BFS. So we'll repeat that, whether the graph is connected, find all the connected components, find the path, the presence of a cycle, topological sorting. Yes, this we'll be doing to the next class day here. So this can be done only by the DFS, not by the BFS. And solving puzzles like maze, this can be done both by the DFS and BFS. Again, the articulation point day here that you should be able to understand, referring to the Google day here. So even this can be done only by the DFS, not by the BFS. Now listing the BFS application, the repeated graph is connected or not, find all the connected components, check the presence of a path, and then so this is one salient feature, finding out the minimum edge path between a given pair of vertices. This can be done only by the BFS, not by the DFS. And also the most efficient way to find all the neighboring nodes is done efficiently by BFS, not by the DFS. Now finding this vertex is a different distance for the BFS day here. So if I start from here, I know that all these vertices can be visited by a distance of 1, and these vertices can be visited by a distance of 2. So this is the DFS. BFS can be used to find out the friends which are at a distance of 1, friends at a distance of 2, and so forth. Now here again, this is the USA, and herein we see that where the servers are located there here, and this will tell us the number of hops. If I want to send a packet from here to here, so it has got to DOCB, it should be WC, so it is everything, it will give a hop. So and now I can use BFS to find out the path that a packet should take, wherein my criteria is it should go with the minimum number of hops. Now lastly, having understood the methods, their applications, how good are these algorithms, and it depends upon the way the graph is represented. So the representation, we know that it can either through the adjacency by adjacency matrix or by the adjacency least. If it's adjacency matrix, it's of the order V square. Adjacency least is of the order V plus E. Certainly on our real life graph, which are sparse, this V plus will be much less than our V square. Now lastly, very often you'll have some kind of a question to compare BFS and a DFS, so which you will be able to understand on your own. Okay, so and then I'll not go through this, so these slides are for only to help you to get those terminologies more